Welcome to today's webinar. My name is Joe Sanders. I'm an applications engineer at M2 Technologies, and my specialty is manufacturing applications. During this event, you will see how to easily go directly from CAD to CAM in an integrated workflow using Autodesk HSM. This will include a live demonstration of Autodesk HSM with a focus on common 2.5 axis and 3-axis milling applications. We appreciate your interest in the topic and carving a few minutes out of your day. This is a live web event and we look forward to your questions. Phones are muted during the presentation and will be opened for Q&A afterwards. If you notice the GoToMeeting panel, it has a question tab, which you can also use to submit questions. We anticipate the presentation will be about 25 minutes. If you are unable to stay, please submit your questions using the GoToMeeting panel so that we can follow up with you later. So what does integrated CAM mean anyway? Integrated CAM is CAM functionality that's inside the CAD environment. So in the case of Autodesk HSM, we're talking about CAM functionality that's inside SolidWorks or Inventor, depending on which CAD platform that you're using. What are the advantages of it? One is that it's a single user interface. CAD and CAM are both together in the same environment. So this is perfect for a user who's already very familiar with the CAD tool and wants to build CAM toolpath in the CAD tool they're already familiar with. Obviously, CAM's used to create CNC toolpath, and in the case of the integrated systems such as Autodesk HSM, the CAM toolpath is added directly into the CAD model. This allows for model associativity, which means that when there's a design change, the toolpath that's already in that file can be quickly updated to suit the latest variant or dimensions of that CAD model. So in the same way that say a sketch or an assembly is associative to model changes, the toolpath in that CAD model also would be. This can be appealing in addition to this because there's a low cost to this technology. It's very easy to pick up and learn as well. And it's a simplified workflow compared to perhaps traditional CAD tools with separate CAM tools. So some users appreciate the low cost, easy to use, and simplified workflow that this CAM option provides. Let's have a quick look at the HSM capabilities. Autodesk HSM package is able to do a wide range of milling work. That runs from your typical 2.5 axis prismatic type applications to 3D applications such as 3D contour milling. 3+2 positioning refers to a machine tool with 4th and 5th axis indexing capability, so it can do the 2.5 axis or 3 axis work from different directions. 4 and 5 axis simultaneous machining capabilities also available, as well as inclusion of touch probes such as a Renishaw probe on the CNC machine. HSM also includes turning capability, both the traditional 2-axis single spindle, single turret lathe, as well as mill turns and even some support for some multi-spindle. And what's called cutting machines, which would be CNC water jets, lasers, and plasma cutters. HSM is able to handle all of these types of CNC machines and be able to build CAM toolpath directly inside the CAD interface. We're going to have a look at that and go through a live demonstration. So I'm going to switch over to Inventor. And in Inventor, I have a suspension for a remote control car. This is one of the samples that's installed with Inventor. Some of you may recognize this from browsing through samples and training classes or other demonstrations. We're going to focus on the area here with the upper control arm. So I'm going to open the subassembly, and I'm going to take this control arm here and directly open that item. Now for ease of visibility, let's change the color. We'll just use a yellow color temporarily. As we have a look at this component, there's three main areas that are the structural areas important to its use in the assembly. And what we're going to do here is we're going to build tool path to mill this in a CNC milling machine. Because Autodesk HSM is an integrated product, notice that there's a CAM tab right inside the Inventor interface. So as I move over to the CAM tab, you'll notice that just like the other tabs within Inventor, there's commands on this panel. So very similar look and feel. Now we're going to begin the machining process by telling the software what we want to do for a part setup. So as I choose the setup command, notice that immediately there's a CAM browser that's added to the interface, and there's a command on the browser to define the setup. The way that HSM works is that each command that we do is going to have a variety of tabs to fill out. The software is very consistent about that, and we'll simply work through the tabs with each command that we do. So to begin with, the software wants to know what kind of a setup we're doing. Notice that as I hover over the setup, there's a graphical help system that helps to convey what the software is asking for information. This is going to be a milling setup. Milling is absolutely appropriate. We'll continue with that. Then in terms of setting zero, there's a variety of ways to set the zero location for the machining setup. So we'll base the z-axis as being perpendicular to that face, and then assign a 0 point at the middle of the stock volume, which is a convenient place for the machinist to pick up the zero system from. We'll tell the software that the model we're using is the solid model. Now notice that there's also an option for fixture. It's possible in Inventor to make manufacturing assemblies that include the finished part, the stock, work holding fixtures, and other things like that that all need to be considered during the CAM environment. While that's an option, it's not a requirement for simple jobs such as this. The intent is certainly that this part would be held inside a vise, and I will build tool path to replicate that intent. But for demonstrations of the simplicity of the product, we're intentionally going to avoid adding a vise assembly to this simply for demonstration purposes. However, keep in mind that that's certainly something you could do. As we go to the stock, instead of a rough size stock based on the finished part rectangular shape, I'm going to go to a fixed size box. And we'll work with stock that's 2 inches by 1.5 inches by 1/2 inch with the part centered up inside there. With this information in place, we'll press OK, and notice that in the CAM browser, we have the first event, our part setup. The first thing I want to do in the machining setup is use a touch probe to quickly update the part 0 based on not only the rough part position, but exactly where that goes. So as I begin the command, we'll see the same common tabs again. And I'll start by going to the tool button, and working from a tool list I have for this, we'll select the probe that we want to use. So we've selected that Renishaw touch probe, and now we'll tell the software what we want to do with it. I want to probe based on the stock, based on the top surface. And the software points us to what's going to happen and suggests different types of probe applications we can do. The part's going to be fairly consistently located, so I'm going to just adjust in the clearance and the over travel to something more suitable for the setup intent. And then on the heights tab, we want the bottom height to be based on the top of the stock, and maybe have the probe running 1/4 inch below that. We can graphically see the height in place. Again, familiar Inventor operation here. After pressing OK, the tool path is built. We can see the tool path in place. That is editable, and we'll show how to do that as we go forward. The next thing I want to do is begin to rough the part. You'll notice that the CAM ribbon inside Autodesk HSM is broken down into different types of machining groups: drilling, 2D or 2.5 axis milling, 3D milling, and so on. The part that we're using here is a fairly common part from a milling perspective in that it has a mix of some drilling, 2D milling, and 3D milling. And as we go through the demonstration, hopefully we'll give you a sense for how valuable it is to have all of those options available. In terms of roughing the part, removing the bulk of material, I want to start with a large tool and remove as much material as possible. We're going to use HSM's adaptive clearing command, which is a proven high-speed roughing toolpath technique. I'm going to start with a 1/2-inch roughing end mill and select that from the database. The database is able to store cutting information such as feed and speed lookup, the tool, the holder, and other information like that. And so because I'm leveraging that, I don't have to spend a lot of time focused on the details. I can think about the big picture of the process that we're putting together instead. As we go into the machining control panel, I'm simply going to tell the software what it is that I'm looking to do, and then we'll go into our working heights. Notice that we can see the working height shown in different colors, which correspond on the screen graphically to the colors here. And those are adjustable, either by clicking and dragging or by direct numerical input. I'd like a 1-inch clearance plane height. I'd like the roughing to consider from the top of the stock, but I don't want to go all the way to the bottom. I mentioned earlier that the part is going to be held in a vise, and from a machining standpoint, the central focus of this setup is to machine a little bit below that lower arm surface. And how much below? Well, for roughing, I'll say 100,000ths of an inch. If I look in from a front view, that looks great. We'll go with that. In terms of depths to machine, we'll let this tool take up to 3/4 of an inch. And I'm really good with, once minimum retractions, I'm good with the rest of the parameters. You can see there's a variety of parameters there that can be used to fine tune and adjust tool path. But in my case here, they're going to be suitable for perhaps refinements, but what I have on the screen is a great starting point. Tool path is built. Now let's take a look at what it does. HSM has excellent simulation. The simulation control bar allows us to have a variety of controls over what we're seeing, and to begin to slow down a bit, and then just press play. Now as the simulation plays, what you're going to see is that the touch probe comes into play. Maybe speed that up a little bit more. The touch probe comes in. It probes the physical actual part location in the vise to make sure we precisely set the zero system at the machine. This will simplify the part setup, and the machinists generally appreciate this being done. Once the probe motion is built, then we're into the roughing. So we can see the roughing tool doing the work. We can see how the material is removed, and we can use the CAD system controls to modify the view as we need to. We can even see, I have what we call a trailing tool display set up, or tail tool display. So we can see just the path that has recently been tracked through instead of having to see the clutter of all the tool path on the screen. But you can certainly adjust that to see whatever you'd like to see. I think importantly, this shows how the material is going to be removed from the part, ensures that there are no collisions, and builds confidence that the tool path being built is what we intend. This looks suitable. We wanted to remove as much material as possible from the part very quickly, and that's been done. This tool is a little bit too large to remove all the material though, and we're going to need to come in with some smaller cutters. Instead of making another adaptive cut and putting in similar parameters, it would probably be fastest to just copy the tool path that we have here and then reuse that by pasting it in and modifying a few parameters. Now, after I've modified it, I've edited it. We mentioned that all of the tool path is editable, and we're going and doing that here. I'm going to switch out and use a smaller cutter. Let's go in with a 1/4-inch roughing tool now. Again, the cutting data is updated as needed. For the main directions of what to do, I'm going to have this do rest machining, or machine what is rest left over from the previous operation. Work heights are all the same. The only major change I want to do is to have this tool machine at 1/2 inch depths of cut rather than 3/4 of an inch as the max. After pressing OK, tool path is built. We can see the tool path working only in the areas that the previous tool left material, and we can go in and simulate that. So as I simulate all, I'm going to fast forward through what we've already seen and focus here on just what we haven't yet. I'm also going to switch the simulation controls so that instead of using the material for colorization, we'll use the tool. This allows us to see where each tool is machined. Each tool is assigned a unique color, and the material takes on the color that is assigned to that tool so that we can see where each tool has done its work. I'm also going to turn off the holder for here. That may help with visualization, and we can see how this tool goes and removes material from places where the previous tool was too large. This is a common process used in many milling shops, where we start with the largest tools possible. Larger tools can remove more material with a little bit less work, and then move down to smaller cutters as needed. The process is coming together fairly well. One place that doesn't have any material removal yet, though, is the void area inside this. It may help if I have the model or the stock be transparent. You can see that area down inside here where the tools have been too large to fit, and so the software is intelligent enough to not be able to put them there. If I close that down, we're going to want to attack that area with a different tool, and I'm going to now switch into the 2D machining. The difference between the 3D commands we've been using and the 2D is that 3D commands work with the part as an entire unit, where 2D allows us to work with specific geometric regions. So when I go to the 2D adaptive, I have the flexibility to target just that area right in there. Let's choose a smaller tool. We're going to need to choose a tool small enough to fit through there, and that's going to be this 1/8 inch roughing end mill. It's a fairly small part and a fairly small cavity. Keep in mind it's from a remote control vehicle. So as I go into the work plane heights here, I really don't want the top to start at the stock. I want it to start at someplace else. We've cleared down to the top of that. And then from a bottom position, we're going to select, and I'm going to select the bottom end of that strut across the part. But then from there, we'll allow the bottom, in this case, maybe the tool can go another 50 thousandths or something like that. We want that to be on the negative side. And we can look in from a front view and again see our work plane heights quite graphically. Looks like I got the wrong numbers in there, probably my bad. So 0 on the top, negative 50 thousandths on the bottom. The graphical height looks much better. That's exactly what we want. Parameters look okay. I do want to remove this right to all the material, remove it right to size. So I'll take off the offset parameters since that's just a weight reduction pocket. And we can see the tool path is now built to completely remove the material from this geometric region using the 2D adaptive command. So good explanation, hopefully, for you of the difference between the approach that sometimes is useful from a 3D perspective and the approach that's sometimes useful from a 2D perspective. They're both available to me as a CAM user. Now that the roughing is out of the way, we're ready to move on to finish milling. I'm going to go back to our 3D commands and begin the process by clearing out the flat floors on the part, and we'll go in and choose a tool. Now actually I'm going to cancel out of this. You can tell that this is live because I jumped the gun a bit. What I wanted to do is demonstrate or show you some of the fillet radius sizes on that and demonstrate that because we're in the CAD environment, we can use the CAD commands we're familiar with. So I'm going to go look at this radius here. The software reports back that that radius is an 0.63. What about that one? That one's 125 thousandths. This type of information is important to the CAM user for selecting tools that can work suitably in those areas. We're able to get that information very quickly using the interrogation ability that's already within the CAM software. And now that we know that information, let's go back to the horizontal command. And that's how I knew that the right tool to use for this is a 1/4 inch tool, but now with a 31 thousandths radius on the nose of that tool. That'll be a good tool for this work. The geometry to machine, we're going to just machine the top of the part, so that'll be fine. I'm going to begin with just saying that we're going to go from the model top to the model bottom. We use pretty common step overs, and again, just use the basic inputs and let the software build toolpath. Notice that it built toolpath not only across the top of that spar or rib, but also at the crowns of the surfaces. The software is correct to build toolpath there, but that's not really a place that I want to machine with this tool. So we can go in and edit the toolpath and further refine it. In this case, we can refine it by going to the heights. And if I look in from say a front plane, and we look at the different heights that we have available to work with here. Let's go to this height here, and notice that I can drag this up or down. Let's drag down till we're just below the crowns, just by eye, and then say that looks good. After pressing OK, we look at the resulting path. Now we have path just across that top face. Great. Let's continue on using the same tool and mill around the outer positions of this. Since we're using the same tool, we'll just continue with the same tool and then put in a few different parameters here. So I'm going to put in some controls for how the boundary around this should work with the part. In terms of machining, we want to machine down to a point based on that bottom face, and maybe beyond that by 50 thousandths now, where you may recall the roughing went 100 thousandths beyond that. Most of the passes here look fine. Have the software build tool path, and we can see that the resulting path now takes that tool and mills around the shapes of the part. I can also see that this tool is large enough to fit into this cavity, and so it goes in there. Well, there's nothing wrong with that. We've already taken care of that, and let's restrict the tool path from doing that. Again, there's ability in HSM to edit and even to go in and add additional inputs such as avoid these surfaces right in through here. So I'll just quickly go pick those model surfaces that we want to keep the tool away from. Just the radiuses at the top will do, because once the software has to avoid those, it can't go in the inside either. And the resulting path looks much better. We're now keeping it out of that area that we've already done the milling in. Great, the process is coming together. Next, let's go into the parallel command where we're going to have a ball mill copy mill this to machine in those radius surfaces pretty quick for us. Again, a common 3D machining technique. We'll choose a 3/8 ball mill. That's a good tool choice for this area. Then in terms of inputs into this, we'll change around the boundaries a bit, for just tool path control purposes. This helps build tool path that moves in the places that I want it to go. In terms of machining in bottom heights, we'll again select that surface and have the tool path be 50 thousandths of an inch beyond that point. I want the tool path passes on this to be about 25 thousandths apart. That may be suitable for our finished work. We'll see. The simulation will help predict that. So you can see this unique motion, this 3D motion is going to be great at replicating this non-prismatic or non-flat base and non-vertical wall areas. We also have the situation where the tool path drops into that area. And again, we can go in and have the software avoid those regions simply by going in and picking those. Zoom in a little bit here to make it easier to pick. So standard picking functionality that you'd be used to on the CAD side of the software. The resulting tool path now stays out of those regions exactly like we intend. Now the reason I didn't want it rolling around those is that I want to attack those areas with a different tool. So we're going to go choose a specialty command. Notice that there's a wide range of choices under both 2D and 3D milling with additional specialty commands on top of the basic ones that we may use day in and day out. So for this one, we're going to go and choose a 16th inch ball mill. And in terms of inputs, we're going to have the software machine around these radius faces that we've been avoiding so far. And then with each of them, I'll make sure that the arrows all point in a consistent, uniform direction. Looks good. And we'll tell it that we want perhaps 5 passes with the tool through that area. Software builds tool path that now runs in the direction around that radius, which will give a nice finish in that area. Let's run a quick simulation on what we built. So we'll simulate everything here, and as before, we'll skip the things we've already seen. We've seen the probe, we've seen the first rough, we've seen the second rough. As the third rough comes into play, we see that tool use a helix move to create its own entry so we can avoid the need for pilot holes. Then open that shape up with the high-speed adaptive roughing. See the end mill come in and clear the flat areas, and then continue on to use the cross-sectional machining, which is great for the steeper walls of the part and for removing some of the material cusps before we do the 3D contour mill work. Speed this up a bit for time purposes. Process looks pretty good. We'll have a nice finish on the walls of the part with this cross-sectional type approach. Now we see the 3D contour mill come into play. See the tool as it works back and forth across here. This will do a nice job of shaping those areas and leaving us with a burr-free part. Then the last piece of tool path where the tool runs around those areas. Let's zoom in. Notice that with simulation, we can even show what we call the cusp heights or material scallop heights. And since this is simply a structural part, it doesn't require the fine detail finish of perhaps plastic injection molds or other very precise 3D contour. This is going to be suitable for what we need for a first setup. So since simulations confirm that this looks good, we're now ready to take this and post-process it. This is where we create the G code for a specific CNC machine. We're going to create CNC code for a Haas machine. That's a fairly common machine that we see. Other posts are available from HSM's post library, and users can quickly make small adjustments to some of the individual flavors of, for example, whether we like block numbers or not, right through that interface. I'll overwrite the code file that's already in there, and here we go. Here's a code file to do all of the work we have here, listing the tools used. We can see the touch probe used to update the work offset, and then begin into the roughing code. There's a lot of tool path that's been built here. It's far more than we would be able to easily build by hand. So everything looks good. Now, that's a quick overview of the process, and again, as we pointed out, this is an integrated system, so it runs right inside the CAD model. If I was to go here and save this part, the tool path is saved directly inside that CAD model. We can close this down. Notice that as we went back to the assembly, I had made the part yellow, and so the assembly now picks up that's a yellow part, and it picks up the mirror image out on the other side because it's a mirror image part. So we've got the tool path built. Software is working in the CAD environment. Let's go back in and edit that and go through a design change process. So in this case here, I'll go edit it and open it directly rather than edit in context of the assembly, simply to show what's going to happen with toolpath. Now I want to point out right now that when we look at the structural thickness of this and we go into the parallel part, what we're going to do is we're going to thin up the structural thickness of this. So right now we've got toolpath where the tool center points that you see shown in blue are moved across the screen. When I go out to the model side and I go find the extrusion that builds the main web across here, so that's an extrusion built to a thickness, then there's a spar that comes across here that's to the same thickness. It's driving off the same dimension. So because of how this is modeled, I'll be able to go edit the feature. We can thin this up from 162 thousandths to 125 thousandths. The spar will thin up as well, the cross brace across here. Everything falls into place. We can go back to CAM. Now at this point, the tool path is not up to date with the CAD design. Notice that it's still up here in the air. But notice also that the software has added a visual indicator to show that the tool path is not up to date with the part. Not a problem. You don't have to start the process over. We're going to simply generate the tool path and have the software recalculate it. So if you think of the tool path in the CAM window as being a process, the question is, does the process need to change because of the design change? And in this case, it does not. The same process we used will still work. We just need to update the tool path to the new part. The software goes and does that. It keeps it up to date for me. This looks good. We're ready to now save this part as a new design and to post-process and build new code. At this point, the CAM process is complete and everything's been tucked inside the CAD system. So here I want to return back to the presentation outside the live demo and explain, okay, so how do we get to the integrated CAM? What you just showed, Joe, and how do we get to that from a license perspective? And if we wanted to try it out, how do we get rolling with it? Inventor HSM is available as part of Autodesk Product Design and Manufacturing Collection. So if you're subscribed to that collection, you're on subscription, you have that product available to you today. Just check out the CAM tab and you should have it there. You can reach out to M2 and talk to us about our quick start program for HSM that includes training, implementation, and technical support on that. And quite simply, it's that easy. This is a very easy product to get started with. Many users find that the uptime on that is very short from the time of first getting rolling with it to the time of creating tool path for your first applications. So as we wrap up, I want to go out and look at questions. If you have a question, let us know. You'll notice there's a... At M2 Technologies, our sales executives, technical advisors, and support team are available to assist with your software applications, questions, and needs. Reach out and put us to work on your challenges. Don't miss out on the opportunity to connect with M2. Follow us on social media for updates, special announcements, and exclusive promotions. You can also watch helpful videos on our YouTube channel and visit our blog for tricks and tips that will boost your productivity.